The probability, we can see it as the bridge that link between the descriptive statistics and inferential statistics. So starting from this chapter, you will start to do some prediction about what we are interested in. So first, we will talk about how we will use the probability to quantify the randomness. So we have some definitions here about the randomness and the phenomena of the random phenomena. So what is the phenomenon? It's anything we can observe, right? Anything we can observe, we call it phenomena. Okay. For example, suppose we have a coin, fair coin, and we already know that 50% we will have a head and 50% we will have a tail, right? After we toss it. But suppose I said to you, toss it for 5 times, 6 times, not 5, 6 times. Do you believe that you will have 3 of them will be heads and 3 of them will be tails after you toss them 6 times? Of course not. Maybe one of them is a head and the others are tails, right? Maybe 3 and 3. Maybe any combination from 1 to 6, right? Why? Because we toss them just a few rounds, few turns, 6 times. But if I say to you, toss them for 5,000 times, in this case, you will start to see that approximately half of them are heads and the other half are tails. So when we talk about the randomness here, we are talking about the randomness for a long run, not for the short run. Okay? Because as I said to you, in probability here, we do what? Prediction. And prediction means expectation. We expect that 50% when we toss a coin, 50% are ahead and 50% are tails. From where we know this theoretical? From the long run. Same thing when we have a die. We already know that we have 6 outcomes when we toss roll a die. Okay? And we know that each one of these outcomes has a probability is 1 over 6. 1 over 6, 1 over 6, 1 over 6, 1 for each one of them. But when we roll a die for 2 or 3 times, of course, we will not have this probability. But if you roll them for 10,000 times, for example, you will find that the probability to have 1 is approximately 1 over 6, 2 approximately 1 over 6, and so on. Okay? So this is what we need to know here about the random phenomena, that we observe this phenomena for a long run to have the correct expectation, not for the small number of trials or for a short run. Okay, so as you can see here, as we make more observations, the proportion of times that a particular outcome occurs gets closer and closer to a certain number we would expect. Okay? So when we observe the number of heads and the number of tails for tossing a coin for a long run, we can see that these numbers are close to 50% and 50%. So this is what we talked about rolling a die, okay, long run behavior of random outcomes. Okay, for example, as one tosses a die in a long run, the number of times a 6 occurs becomes more predictable and less random. It gets closer and closer to 1 over 6. Independent trials. This is something important for some experiments in statistics here, because sometimes we can say we have independent trials, and sometimes we can say we don't have independent trials. So what is the independent trial. Independent trial simply means if an event happens, this will not affect on the other event. For example, if we said that we will toss a coin 2 times, okay? So what do you think? The second outcome, the second toss, will be affected by the first toss? It's not, right? They are separate. They are independent. So in this case, we can say we have independent trials. Okay? But look at the second example now. Suppose we have 3 balls, okay, in a box. Okay? And we wanted to take 2 balls randomly from this box. 2 balls. So suppose these we have the color of these balls is red. So for the first ball, what is the probability that you will get a red ball? Okay, also we have 3 balls in the box, so any one of them will have a probability of 1/3, right? So this is the first one. Look at it. I said what? We need 2 balls, not one. You will not return the first ball to the box. You will keep it with you. Now, start to select the second ball from the box. So what is the probability now? Is it 1/3 or 1/2? 1/2. It's not 1/3. So the probability here gets what? Higher than before. The first one is 1/3. The second one is 1/2. So this is the problem now. When we started to select the first one, after we selected the first one, this selection affects on the second one. So the probabilities are different now. So in this case, we say that these trials are dependent in this case because the probabilities change. But if we select these two balls with replacement, in this case, we can say these are independent trials. Why? Because the first ball will have a probability of 1/3, and you will return it again. The second ball also will be 1/3. So there is no change in the probability. So this is independent trial. So in this example, we can figure out that we have 2 different selections. The first selection is with replacement, the second one without replacement. So if we have the selection with replacement, that means we have independent trials because the selection for the first ball will not affect on the second ball. But if we have the selection without replacement, in this case, the selection or the type of selection here is dependent. Why? Because the first ball had a probability 1/3, the second ball have a probability 1/2. So there is difference in the probabilities, which means that first ball affect on the second, the selection of the second ball in this case. Okay, so we call this independent trials. So this will let us talk about something called the law of large numbers. All of this let us talk about something called the law of large numbers. This is the law of large numbers. Do you know the relative frequency? Do you remember the relative frequency? Frequency table, the classes, frequencies, relative frequency. Okay? So we have do you remember when I said to you the relative frequency is the probability? I said that at the beginning. When we will talk about the probability, you will know the relative frequency is what? The probability. Sometimes we call them the proportions as well. So now we have this. The relative frequency of the number of times that an outcome occurs when an experiment is replicated over and over again a large number of times approach the true or theoretical probability of the outcome. And our example, as I said to you, if you toss a coin 2,000 times. So in this case, you will find the number of heads you have are close to the number of tails. Now we will define the probability. What is the probability? So the probability of a sample point or for an outcome, okay, measures the likelihood that the outcome will occur when the experiment is performed. We can find the probability by three methods, but in your textbook you have two methods. These three methods are the classical probability, and we will talk about it after a while. The relative frequency probability, and this is what we have in the frequency table, okay? And the subjective probability. Subjective probability means an experiment, so you cannot have data, so you cannot measure the probability quite well, but you can make guess about the probability. So this guessing is based on what? Your experience. Okay? So because of that, we call it subjective probability. So let's talk about the relative frequency definition. So it's the long run proportion of times that the outcome occurs in a very large number of trials. But this is, of course, not always helpful. Okay? So if that doesn't helpful, in this case, you must rely on what? The subjective information. So the subjective probability is what? Is the probability of an outcome is defined to be a personal probability, which means it's based on your experience, your guessing, your information you have. You don't have here an experiment to have data. Okay? And then this probability again is really on your degree of belief that the outcome will occur. So based on the available information. So for example, suppose you have a party and one of your friends have emergency case or something. And you know this information. So in this case, you will say, he may come. May is a probability. He might come. Okay? Based on this information. But if you don't know that he doesn't have this emergency case, you will say what? He will come, right? Because you don't have this information. To find the probability, you need to know four things. First, what the experiment. What is the experiment we are usually doing to calculate the probability? So the experiment is the act or process of observation that leads to a single outcome that cannot be predicted with certainty. Like what? Like tossing a coin. When we toss a coin, in advance, you know the outcomes. We have what? A head or a tail, but you don't know which one will live, right? You don't know which one will appear after the tossing. Okay? The sample point. What is the sample point? This is the outcome of the experiment. Like tossing a coin, we know that we have a head or a tail. So these are the sample points. The sample space, this is a very important thing here for the experiment. These are the collection of all possible outcomes. So for tossing a die, we know that we have 6 outcomes. 1, 2, 3, 4, 5, 6. We already know the outcomes in advance. Okay? The event is a specific collection of the sample points. Okay? Or you can from the sample space. Like when we roll a die, suppose we are interested in what? The odd numbers, 1, 3, or 5. As you can see here, this is the example. As I said to you, suppose you will toss 2 coins here. So you already know for each coin you have 2 outcomes, a head or a tail. But for tossing 2 coins, you may have what? 2 heads or 2 tails. Or the first one is the tail, the second one is the head. Or the first one is the head, the second one is the tail. So you already know in advance the outcomes. These all outcomes, we call it the sample space, as you can see here. S is equal to HH, HT, TH, PT, these are what? All possible outcomes from this experiment. Okay, and of course you can um, display these outcomes by any chart, maybe a table, maybe a diagram like this. We call this the tree diagram. So as you can see, the first coin, you will have the first coin here, you will have just two outcomes, a head or a tail. So for the first, suppose the first outcome for the first coin is a head. So the second coin maybe also have a head or a tail. Suppose the first coin has a tail, so the second coin maybe have a head or a tail. So what are the outcomes from these two coins? A head or a head, head, tail, tail, a head, or two tails, as you can see. So these are our sample estimates. We have some properties about the probability. You always see the probability takes values from 0 and 1. There is no negative probability, and there is no also probability more than 1 or 100%. You can say 1%, 100%, or 0%. That means you don't shoot. Okay? So it's between 0 and 1. Something else. So you can say here, for example, I will write this in a mathematical way. Okay? So suppose we can say the probability, we have A. A is an event. So the probability of A, we can say B of A. This means the probability of A, the probability of that event, okay, must be between 0 and 1. Okay? 0, that means never happened. This event never happened. 1 means it will happen. You are sure that it will happen. That means 1 or 100%. Okay? And of course, we have the values between 0 and 1. Something else about our probabilities, the total probabilities must be equal to 1. What that means? That means, look at this example. Simple example. For tossing a coin 1 time, so we have 2 outcomes, right? So we write here the outcomes. Okay, so we may have a head, we may have a tail, right? So the probability of getting a head is what? So we will say here, this is the probability, okay? For getting a head is 1 hand. For getting a tail, it's 1 hand. What is the total of these 2 probabilities? Is 1. Right? So this is what we mean by the total of all the individual probabilities equals to 1, as you can see. Another example. Suppose you have a die. Okay, so the outcomes is 1, 2, 3, 4, 5, 6. The probability for each one of them is 1 over 6, 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 1, 2, 3, 1, 2, 3, 4, 5, 1 more, 1 over 6. So the total is 6 over 6 is equal to 1. So as you can see here, all probabilities between 0 and 1, 1 over 6, of course, is the value between 0 and 1, and the total for all probabilities is equal to 1. Okay? Let me return to this example. Okay? Look at it. Suppose here we are interested in A is the number of heads. The number of heads. Okay? Here you have 2 numbers or 2 heads. Here you have 1 head. Here you have 1 head. Here you have 0 heads. Right? So what are our outcomes? So the number of heads is 0, 1, and 2. Right? Right? Okay. What is the probability now? What is the probability of getting the 0 head? This has happened what? Just one time. And we have how many outcomes we have here? We have 4. So it's 1 over 4, right? Mhm. What about 1 head? This has happened what? 2 times. So the probability will be 2 over 4. Okay? What about 2 heads? It happens here what? Just 1 time. So the probability is 1 over 4. Look at this probabilities. 1 over 4 and 2 over 4. Both are between 0 and 1, right? What about the total? It's what? 4 over 4 is equal to 1. So again, we have the sum of all probabilities is equal to 1. Okay? So these are our properties for the probabilities. All probabilities must be between 0 and 1, and the sum, the total probabilities is equal to 1. Okay? You already know what is the probability of A now, right? So P of A, which means the probability of A, as you can see. Of course, the A is what is the event we are interested in. Maybe we have B. B also is another event we are interested in. We have C, another event we are interested in. So A, of course, the A will have a definition in our problem, and you, based on this definition, you can find the probability. Okay? But the classical probability, usually, we can find it what? By this equation. The number of possible outcomes that constitute event A divided by the total number of possible outcomes in the sample space. Okay? Here, we assume that all outcomes in the sample space have the same chance or the same likelihood of occurring. Like here, in this previous example, here, we suppose here that any outcome of those outcomes is what? 1 over 4, right? This is 1 over 4, 1 over, this is 1 over 4, 1 over 4, 1 over 4, 1 over 4. We suppose that all of them have the same likelihood of occurring. So based on that, we can calculate what the probability. Okay, so we have to have this assumption, as you can see here. Okay, so the assumptions here is what? Each outcome in the sample space has the same likelihood of occurring. So now you can find the classical probability. Okay? And as you can see here, this is the same example we have here. In the experiment of tossing the 2 fair coins, find the probability of observing at least 1 head. So this is what we are interested in. This is what? This is A. See, A here is what? Observing at least 1 head. This is A. The event A. Okay? And we need to find this probability for A. So first you have to have what? The sample space. The sample space is what again? According to our definition, all possible outcomes from this experiment. So what are the possible outcomes? As you can see here, H, T, T, H, T, T. These are all outcomes from this experiment. Which one of them will have it? You don't know in advance. You don't know. Okay? But you know in advance all outcomes. What is the probability of each one of them? Is 1 over 4. Right? 1/4, 1/4, 1/4, 1/4. Okay? Okay. But here we are interested in what? At least 1 head. At least 1 head. So 1 or 2. Right? At least 1 head means 1 head or 2 heads. So here we have 2 heads. Here we have 1 head. Here we have 1 head. Here we don't have any head. So how many times event A happened here? 3 times. Right? 1 or 2 times. So 3 times this event happened divided by the total sample space, 4. So it's what? 3 over 4. This is the probability of A, or the probability that at least one hit will occur. I said will, because this is what? A prediction. The empirical, or sometimes we call it the relative frequency. The relative frequency probability. Okay, the relative frequency probability or empirical probability. How we can find that? First, you have to have what? Huh? The relative, the frequency table. And from the frequency table, you can find what? The relative frequency. The relative frequencies are the probabilities for each outcome we have. So suppose that we have a hotel, ask the customers to rate their stays as excellent, good, fair, or poor. The following table shows the frequency of each rating. We need to complete this table. Okay, so we have here 12 persons rate their staying as excellent, 32 rate their stays as good, 23 rated their stays as fair, and the 8 rated their stay as poor. Okay, this is what the frequency. We need what? The probabilities. So you find what? The relative frequency. The relative frequency here is equal to the probability. So how we can find them? First, find what? The total. And then divide each frequency by the total frequency. So you will have what? The probabilities. As you can see here in the next slides, the total is 75. Divide 12 by 75, so you have the probability. To find 32 divided by 75, you have the probability for good. And again, same thing, the probability for fair, the probability for poor. So in this case, when I give you this question, okay, from this sample, I mean the 75% here, what if, suppose you select a person randomly, what is the probability that this person rated his stays as good? So in this case, you will look at what? The table here. Where is good? Good is here. So the probability is 0.427. This is the answer. Okay? Again, suppose that we selected a person from this sample randomly. What is the probability that he rated his stay as poor? So you will go to poor. What is the probability? Is 0.0107. Okay, another example here. The sample space for an experiment contains 5 sample points with probabilities as shown in this table. So we have 1, 2, 3, 4, 5. These are the possible outcomes. And we have the probability for each outcome, as you can see here. Okay, as I said to you, sometimes the sample outcome, the sample point means the outcomes. Don't get confused. Okay. Okay. Find the missing probability. Oh, we have a missing probability here. Okay, let me change the color. Look, we have a missing probability here. We need to find this probability. Do you remember? 2 things about the probability. All probabilities between 0 and 1. This is the first thing. The second one is the sum of all probabilities is equal to what? 1. So you have to use the second. First of all, you have to make sure that all probabilities between 0 and 1. Look at the first probability here, 0.05. Yes, between 0 and 1. Second one, 0.2. Yes. Third one, 0.3. Fourth one, 0.3. So all this probability between 0 and 1. And the sum must be equal to 1. So you have to use this part. You have to use this property, right? So if you find the sum of all these numbers, find the sum of all these probabilities and subtract it from 1, you will get the missing probability, as you can see here. So it's the missing probability is 1 minus the sum of all probabilities we already know. So the missing one is what? 0.50. Okay? So simple? Okay. Now, find the probability of A. What is A? You have to have a definition for A. A is the event of either 1, 2, or 3 occurs. So where is 1? 1 is here. This is 1. Where is 2? Is here. Where 3 is here. So what is the probability of A? Is the sum of these 3 probabilities. 0.05 plus 0.2 plus 0.3. So you have the probability for event A. We have another event, B. What is B? 4 doesn't occur. Here you have to think about 2 things. Or you have 2 ways here to solve that. Okay? 4 doesn't occur. That means you can subtract this probability for 4 from 1. Because you already know the total probability is 1. And therefore doesn't occur. So subtract this probability from 1. This is the first way, right? Or 4 doesn't occur means 1, 2, 3, and 5 occur, right? So you can find this also by this way. The probability of B is 0.05 plus 0.2 plus 0.3 plus 0.15. This is for 5. So this is for 1, for 2, for 3, for 5. So you will find the final answer also for this. Okay. So we have some basic rules to calculate the probability for 2 events. These rules are the complement rule, the intersection rule, and the union rule. Okay? Something called the Venn diagram. It's a graph we can use to describe the events we have in our experiment. Okay? And as you can see, Venn diagram is just what? It's a circle. It's a circle. This circle represents what? The event. A or B or C, whatever this event. Inside this circle is the outcomes of A or the event. And the outside this circle is what? The outcomes that doesn't belong to A. Okay? So again, the circle is the event. Inside this event, we have what? The outcome of A or belongs to A. And outside the circle, the outcomes that are doesn't belong to A in this case. So we will start with the union and the intersection between 2 events. So as you can see here, the definition of the union of 2 events, say A and B, for example, is the event that consists of all sample points that belongs to A or B or both. So now what that means? All outcomes in A and B, simply. All outcomes in A and B, this is what? The union between A and B. Okay? And we can see this here in the Venn diagram. As you can see, suppose we have 2 events. So you have A here, this is A, this one, and you have B, this one, this is B. Okay? And as you can see here, we have a small part between them, this part. You see this part? Hmm? In this part, we have the common outcomes between A and B. Okay, so you have two circles, one for A, one for B. Okay, and if they have common events between them, you will have this shape. Okay, you have this small part between them, and in this part you have the common events. Okay, so this part we call it A and B. As you can see here, this is here for the intersection, it's obvious. This is A and B. Okay, this part we call it A and B. But the union is A or B. The union is A or B, as you can see. So according to the union of A and B, we need to find all events in A, all events in B, and or both. So this is or both. This is small thing, the black one. Okay? So this is the union. But the intersection means simply the common events between A and B. That's it. We need just the common outcomes between A and B. That's it. This is the A and B, or the intersection between A and B. So you have to make sure that you understand these two things. A and B is what? Intersection. Okay? A or B, you have union. Okay? And or. These two words are so important to hear. Or union and intersection. Don't forget that. Union means all events in A, all outcomes in A, all outcomes in B, and the common events as well. But the intersection, and you have here just the common events between A and B. That's it. This example will illustrate everything here. As you can see here, we have a die. We toss it one time, and you have here two events. A, you have an even number. What that means, an even number? That means A takes values what? 2, 4, and 6. What is B? Thus, a number less than or equal to 3. Less than or equal to 3. So what is the outcomes here? Will be 1, 2, and 3. Right? Okay. So look at the Venn diagram here. This is A. We said A what? The even number. So inside A, you will find 4, 2, and 6, the even numbers. B, you have what? The numbers less than or equal to 3. So you have 1, you have 1, 2, and 3. Okay? And because 5, this outcome doesn't belong to A or B, so you will find it what? Outside the circles, as you can see here. So 5, this outcome doesn't belong to A or B. Something common between A and B, right? Is what? 2, as you can see here. 2 is the common outcome between A and B. So because of that, you can find it what? In this common area between A and B. Okay. So we already done. Oh no, not yet. Not yet. We already done from A and B. Now we need this to describe A or B for this experiment. What is A or B? What is A or B event here? So A or means union. So or means union, right? And the union, according to our definition, is all outcomes in A, all outcomes in B, and also the common outcomes. So what that means? That means A or B is 1, 2, 3, 4, and 6. This is all outcomes in A and B and all between them. We have also and. Describe A and B for this experiment. And the and means intersection. Okay? So intersection between A and B. What that means? That means we need here the common event between the common outcome between A and B. What is the common outcome here? It's 2. This is the only outcome between A and B. So we have here A and B is equal to. Now you can find the probability for the union and the intersection. According to the classical probability, we suppose that all outcomes here has the same probability, equal probabilities. So we have 1 over 6, 1 over 6, 1 over 6, 1 over 6, for 1, 2, 3, 4, 5, 6, right? So now, what is the probability of 1? It's 1 over 6. The probability of 2, 1 over 6. Probability of 3, 1 over 6. 4, 1 over 6. 6, 1 over 6. How many? We have 5. So you have 5 over 6. So this is the probability of A or B, or the probability of union between A and B. For and, what is the probability for A and B? So again, for A and B, we have just one outcome, is 2. So what is this probability? Is 1 over 6. So because of that, we have here the probability of A and B is equal to probability of 2, so it's equal to 1 over 6. Another example, family planning perspectives reported on a study of over 200,000 persons in New Jersey over a recent 2 years period. The study investigated the link between the mother's race and the age at which she gave birth, called maternal age. The percentages of the total number of persons in New Jersey by the maternal age and race classifications are given here in this table, table 4.3. Define the following events. First, A is what? A New Jersey birth mother is white. B, a New Jersey mother was a teenager when given birth. So we have here 2 different events, A and B. A is what? A New Jersey birth mother is white. The B event is a New Jersey mother was a teenager when giving birth. So now we need to find what? What is the probability of A? Find the probability of A. So again, we turn to the definition of A. A New Jersey birth mother is white. Okay, so where is white in this table? As you can see in this table, the race is here, white, black, and the maternal age, as you can see here, less than 17, 18 to 19, 20 to 29, and more than or equal to 30 years old. Okay? A says what? The mother is white. That's it. Regardless what? The maternal age. Just white. So, from here in this table, this is white. For this column is white. So, the probability of A is what? Is the sum of all these percentage. Okay? So it's 2 plus 3 plus 41 plus 33. Or you can convert them to proportions. 0.2 plus 0.3 plus 0.41 plus 0.33. So this is the probability of A. Okay? Okay. We need also the probability of B. What is B first? A New Jersey mother was a teenager when giving birth. So what? huh, So from the maternal age, you can know the ages of what? The teenager, right? And regardless what? The race. huh. So 17 or less. Are these teenagers? Yes. 18, 19. Same thing? Yes. 20, 29. No, they are not teenagers now, right? So we have just these two ages. We have these two ages now, less than 17 and 18 to 19. Okay? Now, what is the probability? As I said to you, a New Jersey mother was a teenager when giving birth, regardless the race. B doesn't talk about the race. So here, so what is the probability now? Will be the sum of these four probabilities. Why these four? Because this is for just less than 17 and 18 and 19 regardless of the race. So will be 2% plus 3% plus 2% plus 2%, or zero point 0.2 plus 0.3 plus 0.2 plus 0.2. So this is what the probability of B. Okay. Of course, you can see these answers here. You can see. Huh? So again, A, New Jersey birth mother is white. This is white. So here you have the probability of A, the sum of this term. Same thing. For B, B is what? A New Jersey mother was teenager when giving the birth. So the probability of B is the sum of these four probabilities. Okay. Now let's talk about find the probability that between A or B. A or B. Again, or means union. Or means union. So what that means? We need to find here the union between a New Jersey birth mother is white and a New Jersey mother was a teenager when giving birth. So what that means? All events in A, which means white. All events in B, which means huh, teenagers, just the teenagers. Okay? Or both. So which percentage we need to use here to find this probability from this table? So 0.2 here, or 2% and 30%. These two percentage, 4, and these are the common events between A and B. Because A said what? The mother is white. B is what? It's a teenager. So the common event between them is this 2%. Huh. But we need or. Or means what? White or teenager or both. So for the teenagers, we have those probabilities. For white, we have this column. Do you see what I did here? I draw here two, can say two circles. Two circles. One around the teenager age and the other one around what? Around the white. So in this case, what are the probabilities should I use here to find the probability of A or B? 2%, 3%, 41%, 33%, 2% and 2%. That's it. So you have the or, as you can see. No? So here you have 2% and 3%, those. Okay? 41 and 33, those. And the remaining is what? 2 and 2. Okay? So this is what or in this case. The third rule is the complement rule. And as you can see here, if you remember, I said to you when I talked about the diagrams, the Venn diagram, I said what? You have a circle, and this circle represents the event. You have A, and inside this event, we have the outcomes belongs to A. Any outcome outside this circle is what? Is A complement. So what is A complement? Is, as you can see here, all sample points or outcomes that are not in event A, doesn't belong to event A. Any outcome doesn't belong to event A, it's A complement. It's with A complement in this. As you can see here from the Venn diagram, you have A and the A complement, and both form what? The entire sample space. The entire sample space. Right? A and A complement, as you can see here, S is equal to A and A complement. S is equal to A and the A complement. As you can see here, the sample space here consists of these two events. So what that means, if you try to find the probability for these two events, the probability for S and is equal to the probability of A plus probability of A complement, the probability of the sample space always equal to 1. Always. The probability of the sample space is equal to 1. Always. So you can have this rule. The probability of A plus probability of A complement is equal to 1. So what that means? That means if you know the probability of one of them, you can find the other one. How? By this rule. If you know the probability of A complement, you can find the probability of A, it's 1 minus the probability of A complement. And same thing, if you know the probability of A, you can find the probability of A complement is equal to 1 minus the probability of A. As I said to you, just you know one of them, you can find the other. Okay? So this is the complement rule. For example, consider an experiment of tossing pair coins. Okay. Define the following event. A, observe at least one head. Okay. A, observing at least one head. So that means 1 or 2 or 3, whatever. Find the probability of A if 2 coins are tossed. 2 coins are tossed. Okay. So first, what is the sample space for this experiment? So S is HH, HT, TH, TT. Right? Okay. We need the probability of observing at least one head. One head. So we have here 2, we have here 1, we have here 1. Right? We have here 0. Correct? So what is the probability now? So when we toss the two coins, the probability of A is probability of 1 plus probability of 2. Probability of 1 is, this should happen what? 2 times. So it's 2 divided by 4 plus 2 happened just one time, so it's 1 over 4, so it's 3 over 4. So this is the probability of A observing at least one head when we toss the coin 2 times. Okay? Look at the second one. Find the probability of A if 10 coins are tossed. Oh, 10 coins? In this case, we have a problem, right? What is the problem? This is the sample space. S. How you will write the sample space now? Because each outcome will consist of 10 combination of H and T, right? For example, the first outcome, all of them are H. Another one, all of them are T. Another one, the first one is H and the rest are T. And you will do the combinations, right, for them. Oh, it's a lot. I said it's a lot, but we can count them. Can someone let me know how many outcomes will be in this sample space when we toss 10 coins? Look at it, the first question. Look at the first question. The first question here, when we toss 2 coins, we already have what? 4 outcomes in the sample space, right? So 4 is what? 2 by 2 or 2 times 2, right? 2 times 2 is 4, right? Or, oh, no, I mean, you have 2 times 2 is 4, right? Or 2 is 4, right? Right? So both gives you the number of sample space, right? Okay. But this one tell us something. Try to tell us something. We have 2 power 2. The first 2 is what and the power is what? 2, this one, the number of outcomes for each coin. So this 2 is the number of outcome for each coin. What about this 2? The number of coins, the number of coins, the number of coins. That's right. So now, can you know how many outcomes in the second example, which means when we toss the coin 10 times, or oh, sorry, when we have 10 coins, so will be what? So the number of outcomes in the sample space S is 2 power what? 10, 20. Okay? So this is the total outcome. Now, we need to find the probability of A. What is A? Observing at least one head. So maybe we have 1 head, 2 heads, 3 heads, 4 heads, 5, until what? Until 10, right? So what do you think? From 1 head to 10 heads, these are what? the outcomes in the sample space, all of them except what? Except one. One is missing here. Which one? All are tails, right? This is the only missing one now, right? Again, look at the sample space here. Here you have what? One, one, two, and zero, right? Same thing. When you have 10 coins, you will have what? One head many times, two heads many times, three heads many times, until just one will be 10 heads. And what? No heads, right? All are tails, correct? And this probability is equal to what? The probability that you will not have a head, which means all are tails, is equal to what? All are tails, or 1 over the total number of sample space, right? Like here. Huh? What is this probability? The probability that all are tails. It's 1 over 4, right? So the probability now. So this is what it's like what? It's the probability of A complement. So you know now the probability of A complement. So what is the probability of A? Is 1 minus probability of A complement. So it's 1 minus 1 over 102 24. When we toss two coins, the sample space is, as I said to you, two edges, one edge tail, and two tails. Right? This is the sample space. What is A? A at least observed in one head. At least observing one head. One, which means one or two. So we have two here, one and one. So these are A, as you can see here. So what is the remaining? It's A complement in this case, which is T and T, right? What is the probability of T and T, the A complement? It's 1/4, right? So use it to find the probability of A. So the probability of A is what? 1 minus 1/4, so it's a 3 over 4. Or you can find it by the way I did before. It's what? You have here 3 outcomes, so it's a 3 over 4. That's it. Okay? Okay. What about when we have 10 coins? So you will have the same sample space, right? But this time you have, for each one of them, you have 10 H and T's combinations. Okay? For example, S, for the second example, or for the second one here, you will have all of them are T's. This is the first outcome. The second outcome is what? H. Okay? What is the third one? And you will continue by this way. But you will do this how many? 1,024 times. You wait 2 days until you finish. Okay? But we have a simple way to find this probability. How? like we did in the first experiment when we have two coins. We already know that uh, the only outcome will be outside A event. A event is what is all of them are T. This one, we know that, right? So what is the probability that all the 10 coins are tails? 1 divided by 1024. This is what the A complement. So now you can find the A because as I said to you, if you know one of them, you can find the other. What is the other? At least one. Head, right? So this is the A. So the probability of A is what? Is 1 minus the probability of A complement. You already find the head. So it's 1 divided by 1024. So will be this one or this one. That's it. This is the idea. That's it. Okay? Is it obvious now a little bit? So you get it? Okay. So the idea here is too simple. Okay? We already know that no heads will happen just one time. In the samples, in the entire sample space, all outcomes we have here, just one of them will have, all of them are tails. This will happen just one time. Okay? So if you find this, the probability for this outcome, this will be what? A complement. Why A complement? Because we are interested in at least one head, which means the rest of the outcomes. Okay, from 1 to 10 heads. So just so you know, the A complement and its probability, it's 1 over the number of sample, the outcomes in the sample space. Okay, 1024. So you can find what the probability of A, which is the probability that at least one head will appear. Okay. Disjoint events, and sometimes we call it mutually exclusive events. So when we have A and B, these are two events, and we can say they are disjoint if you don't have any common events between them. So when we draw the Venn diagram for these two events, there is no common area between them. Nothing. We have separate circles, as you can see here. Okay? Nothing in between. Nothing. Separate. So in this case, we call these two events disjoint events or mutually exclusive events. Okay? When we have mutually exclusive events or disjoint events, the probability of A and B, the intersection is equal to what? To 0, right? Right, nothing in between them. So no outcomes in between them. So it's a 0, right? So the additive rule, which is the probability of A or B, is equal to the probability of A plus probability of B. Simply. Just find the probability of A, the probability of B, add them together, so you have the probability of A or B, the union between A and B. Okay? But if they are not disjoint like this, so the additive rule is the probability of A or B is the probability of A plus probability of B minus the probability of A and B. Do you remember we talked about this one? Why here we have minus? Because when you add the probability of A to the probability of B, you add the probability of A and B twice. So you have to remove one of them. So because of that, we have negative probability of A and B. And of course, if A and B are disjoint, that means this part is equal to 0, so we don't have it. Like here. As you can see, what is the difference between this rule and this rule? Probability of A or B, probability of A or B. Probability of A plus probability of B Here also probability of A plus probability. The only difference between them is what? Minus the probability of A and B. If they are disjoint events, this means the probability of A and B is equal to 0, so you don't have this part. But if they are not disjoint, of course, you have to remove one probability for the common events, as you can see. Okay? So these are the additive. For example, hospital hospital records show that 12% of all patients are admitted for surgical treatments. 16% are admitted for obstetrics, and 2% received both obstetrics and surgical treatments. If a new patient is admitted to a hospital, what is the probability that the patient will be admitted for surgery, for obstetrics, or for both? Because we have here, or both, that means we are talking about the union between these two events. We have here two events, right? These two events are the surgical treatment. This is the first event, A. The second event that the patient will admitted for the obstetrics, okay? And between, and the patient will receive both treatments as well, as you can see. So what we have here is, if we consider this A and consider this one is B, and of course, because we have here and, so this is A and B, and we need to find the union between them. So you will apply the additive rule, of course. As you can see here, you have the probability of A is 12% or 0.12, probability of B 16% or 0.16, and the probability of A and B is 2%. And we need to find the union between them. So you will apply the additive rule for not disjoint events, as you can see, because we already have a value for the probability of A and B. So A and B are not disjoint events. Apply this rule. So you have 26%. The patient will be admitted for surgery or obstetrics or both together, as you can see. Another example, but this example talks about if the events are disjoint or not. So, A, we have this experiment of tossing two fair coins. So A observed two heads. Okay, so A is equal to what? Observe two heads, which means H and H. B, observe at least one head. So A is equal to, or B, sorry, B is equal to what? H, 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 T, and TH. C, observe two tails. So C is equal to what? T and T. Right? Okay. So find the probability of A or B. A or B. So from here, you can find the probability of A is equal to 1/4, right? And the probability of B, as you can see here, is what? 3/4. Is there any common events between A and B? Yes, we have. H and H, right? So the probability of A and B is 1 over 4 because it's H and H, right? So what is the probability of A or B now? So the probability of A or B now is equal to probability of A plus probability of B minus the probability of A and B. Okay? So we will have here 1/4, 3 over 4 minus 1/4. So it's a 3 over. Okay? Same thing. Find the probability for B or C. The probability of B or C, which is the union between B and C. So B has what? H, 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 T, T, H. C just has T and T. Is there any common events between them? No, there is no common event between them. So what that means? That means the probability of A and B and C is equal to 0. So how we can find the probability now? So the probability for B or C is equal to probability of B plus probability of C. The probability of B we already have it. It's 3 over 4. And the probability of C is 1 over 4 because we have just one event. So it's one outcome. So it's equal to this. So this probability is equal to 1. As it is. So according to the results in A and B, what do you think? A and B are disjoint events or not? According to the definition of the disjoint events means there is no common events between the events. So what do you think? A and B are disjoint events or not? They are what? They are not disjoint. Very good, because we have H and the H common events between them. Okay? What about B and C? Are these two events disjoint? They are, because there is no common events between them. What about A and C? Is there any common event between them? No, so they are disjoint events. Okay? So according to that, you have here two events are disjoint, B and C and A and C. And of course, you have the answers in the next slides as well. Okay, let's return to our example about the hotel. Okay, remember a hotel asks the customers to rate their stays as excellent, good, fair, or poor. The following table shows the frequency of each rate as well as the gender of the customer. What is the probability that a randomly selected customer was a man who rated his stay as good? Look at men. And they rated as good. So it's a man and rated his rate as good. How many? How many did that from the table? A man and rated his stay as good. How many? 20, right? So the probability is what? 20 divided by 75, the total number of the customers. Okay, so this probability is 20 divided by 75. Okay, look at it, the next one. What is the probability that a randomly selected customer either was a woman or rated his or her stay as fair. Look at either and or. So here we need what? The union. The union between two events here. What are these two events? The event that the customer is a woman, and the second event stays his rate or her rate as fair. So these are the two events here. So we need here to make sure, are these two events disjoint or not? We need to know that. So first, find the probability that the customer is a woman. So this probability is, of course, regardless of the rating. Okay, how many women we have here? How many women? We have 30 women. So the probability will be 30 divided by 75. The second event stay the rate as fair. So the probability of fair. So look at fair. Fair. The total is what? 23, right? So we have 23 divided by 75. Now, do we have any common events between the customer is a woman and rated her stay as fair? Very good. 7. We have 7 of them. Yes, 7. As you can see, the women are here, the fair is here, and we have these 7 people, 7 customers are women and rated their stay as fair. So this is the probability of women and fair. And this one is equal to 7 divided by 75. So now you have what? The probability of A, which is women, the probability of fair, which is B, and the probability for both. So now you can find the probability for the union, because it's said either was a woman or rated his or her stay. So or here means we need to find the union between them. Okay? So as you can see here in the next slides, the answer will be the probability of the woman plus the probability of the customer rate his stay or her stay as fair, and minus the probability for a woman and rated her stay as fair. So you have 61% for this event. Another example. Consider a family with 2 children. The sample space for possibilities for the gender of the 2 children are, maybe they have 2 females, 2 males. The first one is a female, the second one is a male, or the first child is male and the second child is a female. Assume that the 4 outcomes in the sample space are equally likely. We know that because we are dealing with classical probabilities. So each one of them has a probability 1/4. Let A is equal to what? The first child a girl. The first child is a girl. And B, the second child also is a girl. So what is the probability of A? The first child is a girl. So as you can see here, we have a female here. The first child is a female. Also here, the first child is a female, right? So we have 2 of them. So it's 2 divided by 4, right? 2 divided by 4. The second B, the second child is a girl. Okay, so where is it? So we have here the second child is female, and here also the second child is a female. So that happened twice. So also we have here 2/4. Okay, now between A and B, is there any common events between them? Yes, we have. We have what? Female and female. Both childs are female, right? So in this case, what is the probability of A and B? This is happened just one time, so it's 1 over 4, right? So now you have what? We need to find what? The event of A or B is the event that the first child is a girl and the second child is a girl, or both. Okay? Or we can say at least one child is a girl. It's also the same thing. So how we can find this probability? We use the additive rule. The probability of A or B is equal to probability of A plus probability of B minus the probability of A and B, and we already calculate them or found them. So you have 75% the probability of the first and the second, or the second child are girls. The independent events. If you remember, I talked about the independent events or at the beginning of the class. I said what? If you have two events, okay, so the occurrence of one of them doesn't affect on the second one. So this is our independent events directly. Simply like that. Okay. But if one of them affects on the probability of the occurrence of the second one, this of course dependent events. Okay. Simply it's like that. We have something called the multiplicative rule. Multiplicative rule, as you can see here, if you have two independent events. So look at this. Look, we have independent events. Okay, so the intersection between them, which means and the probability of A and B is equal to what? The probability of A times the probability of B. Okay, so because of that, we said it's multiplicative because we use the multiplication when we calculate this event, or the probability of this event. Okay, for instance, suppose you have two die and you will rule them. What is the probability there? You will have 6 on the first rule and another 6 on the second rule. Because we have separate rules here, right? So they are separate die. Okay. So in this case, two rules. So we have two rules. They are separate. They are independent. This will not affect on the probability of this. So in this case, you use the rule of the multiplication rule here. As you can see, 1 over 6 times 1 over 6. This is the probability that you will get 6 when you roll a die one time. So it's 1 over 36, as you can see. Okay. Of course, we can extend this rule to more than 2 events. So suppose we have A, B, and C, 3 events or 4 events, and then all of them are independent. There is no dependent events among them. So you can apply the multiplicative rule as well, like this. So suppose you have here, what is the probability of getting the 3 questions correct by guessing? Or you have 3 questions, they are not independent questions. And you will guess what is the correct answer. So suppose for each question you have 5 options, and one of them is the correct one. Okay, one of them is the correct one. 5 options. So what is the probability of the correct answer? Will be 1 over 5. You have 5 options, right? So the correct answer is 1 over 5. What is the probability of wrong answer? 4 over 5, right? That means here you have 3 questions and they are independent. So what is the probability that you will guess correctly the 3 questions? They are independent. So the first question is correct, the second question is correct, the third question is correct, So it's 1 over 5 times 1 over 5 times 1 over 5, right? So you have 0.008. So this is the probability that a student can guess 3 questions correctly, as you can see. If but what if you have 5 options? Of course, if you have 4 options, this is completely different probability in this case. Okay. Okay. Of course, in this diagram, you have all possible outcomes for the correct and wrong answers, as you can see here. You have the 3 questions. Question number one, question number one, question number two, three. Of course, for the question number one, you have just 2 options, correct or incorrect. So the correct is 0.2, the incorrect is 0.8, which is 1 over 4, 1 over 5, and 4 over 5. The second question, of course, after we assume that the first one is correct, so the second question also, you may have a correct answer or incorrect answer, but with the same probabilities. Again, if or we assume that the first question is not correct, so you for the second question, because they are independent, so you still have the same 2 probabilities for the correct answer and incorrect answer. Same thing for the third question. So now the sample space, as you can see here, maybe all are correct. Here you have 2 correct answers, 1 incorrect, or same thing here, same thing here, and for 2 wrong and 1 correct answer here and here and here, and the last one, all of them are incorrect answer. So these are all possible outcomes for this uh, experiment. And as you can see here, because we have here independent question, so you will apply what? The multiplicative rule. So you will multiply 0.2 times 0.2 times 0.2, so you have the first one. Or 0.2 times 0.2 times 0.8, so you have the second probability for the second event here. Same thing for all, so you have here all of them. As you can see here, all probabilities here between 0 and 1, and you will find that the sum of all of them is equal to 1, for sure. Okay? Okay. This is another question. What is the probability that a student answers at least 2 questions correctly? So at least 2 correctly, which means at least 2 or 3, right? At least 2 or 3. Okay, so from the diagram there, you will find what? Huh? At least 2. So we'll start with 2, right? So 2 correct. So you have this. You have this. And also you have this. So these are the probabilities for 2 correct answers. But this is the at least. Or 3. So also you will take 3 correct answers with them. Okay? So in this case, you will add these probabilities together. So you have the required probability, as you can see. So what that means, in summary, there is only about 10% chance of passing the test, or if the test just has 3 questions, when a student randomly guesses the answers. Okay. So as I said to you, if the 2 events are not independent, that means one of them affect on the other one. Okay. So in practice, events need not need not to be independent. For some examples, we will talk about them after a while. Okay. So suppose you have these are not independent events. Suppose you have here a quiz with only 2 multiple choice questions. Just 2 questions. Okay. So in this case, you have the incorrect and the correct answer. The outcome, as you can see here, you can have two incorrect answers. The first one is correct, the second one is correct, or the first one is correct, the second one incorrect, or both are correct answers. Okay, and you have the probabilities for each outcome, as you can see here. For the first outcome, this is the probability 0.26. For the second outcome, you have 0.11. For the third outcome, you have 0.05. And for the last outcome, you have 0.5. Okay? Or you can write down or make a table for these two questions. Here's the first question, the second question. Okay? If correct and incorrect, this is of course the classification for each question, correct and incorrect, and you can put the probabilities in the table as you can see. Okay, so now the question is define the events A and B as follows. A, first question correct. B, second question correct. So A is what? First question correct. B, second question correct. So what is the probability of A? First question correct. So first question correct. Okay. And regardless, we don't ask about the second question. So you may have what? C or CI, right? The first question correct. Okay. So you will add these two probabilities together, so you have this. Same thing for B. The second question correct. The second question correct. So you may have C or IC. The more important thing, the second question is correct. So you will add these two probabilities together, so you have the probability of B as you can see. Do we have any common events between them? Yes, we have C and C. So what is the probability of A and B? Will be C and C. Where is C and C? It's here. C and C. 0.52. So this is the common events between them. Okay? The question is, are A and B independent or dependent events? If A and B are independent events, so you will have this. The probability of A and B is equal to the probability of A times the probability of B, which means the left side is equal to the right side. Let's do this. We already have the left side, right? 0.58. What about the right side? So multiply the probability of A, 0.63, times the probability of B, 0.69. How much? 0.43. So it's not equal to the left side, right? So A and B is what? Are not independent. Are not independent or dependent events in this. Okay? So that means if they are independent, the left side is equal to the right side in this equation. Okay? Okay. So this is a way to check if the two events you have independent or not independent. So this is the end of the first part in the probability. Okay, we are done from there, and we will continue the second part next week